Welcome to our comprehensive guide on marginal analysis in Stata, a presentation specifically designed for university and graduate level economics students and researchers. Throughout this session, we will navigate the entire process of marginal analysis, starting from the initial estimation of your statistical models all the way through to the meaningful interpretation of your results. Our focus will be on practical applications using Stata versions 18 and 19. The aim is to bridge the gap between complex model coefficients and clear, actionable insights, enabling you to effectively communicate your findings. Let's begin by exploring how marginal analysis can transform your research. In many nonlinear models, such as logit or probit, our raw regression outputs often present coefficients in scales that are not directly interpretable. For instance, a coefficient of 0.54 from a logit model represents log odds, which is mathematically correct but very difficult to explain to a non-technical audience or derive actionable insights from. Marginal analysis serves as the crucial key to bridge this interpretation gap. By applying the derivative, it translates these abstract parameters into intuitive and actionable metrics, such as a 12 percentage point increase in probability or a $500 change in an outcome. This transformation is essential because while the term marginal effect in statistics can sometimes imply an integral, in economics, it consistently refers to an additional or incremental change, which is mathematically a derivative. We critically need this tool to convert complex model outputs into clear, actionable probabilities. To effectively apply marginal analysis, we follow a clear decision framework. The starting point is always to identify the type of your predictor variable. If you're working with a continuous variable, such as age or income, the marginal effect is derived using calculus, specifically a derivative. This gives us the instantaneous rate of change, or the slope, of the outcome with respect to that variable. However, if your predictor is a categorical or discrete variable, like gender or union status, we calculate a first difference. This means we compare the outcome when the variable switches from one level to another, yielding an incremental effect. After determining these individual effects, the next crucial decision is how to aggregate them across your sample. This leads to three primary aggregation methods: the average marginal effect, the marginal effect at the mean, or the marginal effect at representative values, each suitable for different analytical goals. We will explore these aggregation options in detail next. After calculating individual marginal effects, we need to decide how to aggregate them into a single summary measure. This slide outlines the three primary options: average marginal effect effect at the mean, and marginal effect at representative values. The average marginal effect, AME, is often considered the gold standard. It computes the effect for every single observation in your data, then averages those results. This approach inherently respects the actual distribution of your data. In contrast, the marginal effect at the mean, MEM, first averages all predictor variables to create a hypothetical average person, then calculates the effect only for this person. While simple, this average person may not truly exist in your dataset. Lastly, the marginal effect at representative values, MER, is ideal for testing specific hypotheses. Here, you compute the effect at distinct chosen values of your variables, such as comparing effects for low-income versus high-income individuals. This reveals how the effect changes under different conditions. AME, as noted, provides a natural summary that respects data distribution. With these definitions clear, let's now briefly delve into the underlying mathematics Stata uses. As a leading expert in the field states, Stata's margins command is worth the price of Stata. It's truly awesome. This sentiment is echoed by many researchers because of its robust approach to marginal analysis. The critical component enabling this power is the delta method. When we compute marginal effects, we're essentially performing a nonlinear transformation of our initial regression coefficients. The standard errors from our original model no longer directly apply to these transformed effects. The delta method is a sophisticated statistical technique that precisely recalculates and adjusts these standard errors, accurately accounting for the uncertainty introduced by the nonlinear transformation. Stata automates this entire complex process. It takes your raw coefficients, applies the necessary calculus and the delta method, and then outputs marginal effects with correctly adjusted standard errors. This automation is crucial, as attempting to calculate these by hand would be incredibly complex and prone to errors, jeopardizing the validity of your inferences. The mathematics behind marginal effects vary depending on whether we're dealing with continuous or discrete variables. For a continuous variable, like age or experience, the marginal effect is precisely the partial derivative of the predicted outcome with respect to that variable. This represents the instantaneous rate of change, or the slope of the tangent line at a given point on the function. Stata calculates this using a two-sided numerical derivative. In contrast, for discrete variables, such as a binary indicator for union membership, we cannot use a derivative. Instead, we calculate an incremental effect, which is the discrete difference in the predicted outcome as the variable switches states, typically from 0 to 1. This means we compare the predicted probability of an event when the variable is 1 against when it is 0. Both of these approaches are fundamental to how Stata's margins command translates coefficients into interpretable effects. This slide introduces the single most critical rule for effectively using Stata's margins command, the golden rule of factor variables. To ensure Stata correctly calculates marginal effects, you must use its built-in factor variable notation when you specify your model. This means using I dot for categorical variables, C dot for continuous variables, and operators like hash hash or hash for interactions and polynomials. The reason this is so crucial is that this notation explicitly tells Stata the true functional relationship between your variables. For instance, if you're modeling a quadratic effect of age, using c.age hash hash c.age signals to Stata that age and age squared are inherently linked. This allows Stata to correctly apply calculus, like the chain rule, when computing derivatives. In contrast, if you manually generate a squared term, such as gen age squared equals age times age, Stata treats age and age squared as two entirely distinct and unrelated variables. Consequently, any derivatives it attempts to calculate for marginal effects will be incorrect, as it won't recognize the underlying quadratic relationship. Adhering to this rule is fundamental for accurate marginal analysis. One of the biggest challenges in statistical modeling is translating complex coefficients into language that's easily understood by everyone, especially non-technical audiences. This slide provides a powerful template for doing just that when discussing marginal effects. When you interpret a marginal effect, you can articulate it as a 1-unit increase in your predictor variable x is associated with a y percentage point increase in the probability of your outcome z, holding all other factors constant. This breakdown clearly identifies the scale of the change in the predictor, the magnitude of the effect on the outcome, and the specific event being targeted, while reminding us of the ceteris paribus assumption. It's crucial to distinguish between odds ratios and marginal effects. While odds ratios are about likelihood and are mathematically precise, they are often difficult for laypeople to intuitively grasp. Marginal effects, by contrast, speak directly to changes in probability, making them far more effective for policy briefs and public communication, bridging that interpretation gap we discussed earlier. Remember, these effects describe what the model predicts, and establishing causality is a separate research design challenge. The margins command in Stata is incredibly flexible, allowing us to specify exactly how we want to calculate and present our marginal effects. Let's break down its core components, as shown here. The first part, margin list, which is optional, is where you specify the variables for which you want to understand the effects, such as race or sex. Next, dy/dx var list is the engine of the command. This option explicitly tells Stata to calculate the derivative for continuous variables or the discrete difference or categorical variables, transforming raw coefficients into interpretable effects. Then we have the @var equals value option, which sets the scenario. It allows you to fix other variables at specific values to calculate conditional marginal effects, which is particularly useful when implementing a marginal effect at representative value, or MER, as discussed earlier. To give you a concrete example, the command margins dydx education at age equals 30 asks Stata, what is the marginal effect of one additional year of education specifically for individuals who are 30 years old? This helps us answer very precise what-if questions. Other useful options include @means for mem, over varname for subgroup analysis, and post to save results for further commands like etable. Beyond the basic margins command, Stata offers several powerful options for a more granular and robust analysis. First, the @means option is used to calculate the marginal effect at the mean, or MEM. This sets all covariates to their mean value, essentially creating a hypothetical average person, and then calculates the marginal effect for that specific profile. Next, the over varname option is critical for subgroup analysis. It allows you to calculate and present marginal effects separately for distinct groups within your data, such as for men and women, providing tailored insights. For researchers working with complex survey data, VCE unconditional is crucial. This option ensures that the variance-covariance matrix accounts not just for the sampling distribution of the parameters, but also for the sampling distribution of the covariants themselves, leading to more accurate standard errors. Finally, the post option is incredibly useful for subsequent analysis and reporting. It stores the margins results in Stata's E-matrix, making them accessible to other commands like test for hypothesis testing, or the E-table command for creating publication quality tables, as we saw earlier. Before we dive into a full case study, it's crucial to review a quick data preparation checklist to ensure our margins command yields accurate and meaningful results. First, always check for missing data. The margins command, like your estimation model, operates only on the estimation sample, meaning observations with missing values will be silently dropped. Using mistable summarize can help you identify these. Second, verify your variable labels. Clearly labeled categorical variables, such as 0 equals male, 1 equals female, significantly enhance the readability of your output tables. Third, always check the bounds of your continuous variables using the summarize command. Knowing the minimum and maximum values helps you select sensible @values for conditional marginal effects and prevents extrapolating beyond your data range. Finally, and this is a critical point we emphasized earlier, ensure your model strictly uses Stata's factor variable notation, like double hash for interactions, rather than manually creating these variables. This allows Stata to correctly compute derivatives for marginal effects. We are now moving into our first case study, where we'll apply the concepts of marginal analysis to a real-world scenario. Our goal is to predict high-wage earners using the National Longitudinal Survey of Women, or the NLSW88 dataset. The core research question here is, how do union status and work experience affect the probability of being a high earner, defined as someone with a wage greater than 15? We begin by running a logistic regression model. Our dependent variable is high wage, and our predictors include union status and total experience, which we've modeled with a quadratic term, c.ttlexp #c.ttlexp, to account for potential nonlinear effects. As you can see from this data output, the coefficients, like the 0.540 for union status, are presented in log odds. While statistically valid, these log odds are not immediately intuitive or easy to interpret in terms of changes in probability. This is precisely where marginal analysis, using the margins command, becomes invaluable. Now that we've established our logistic regression model, our initial step in marginal analysis is to compute the average marginal effects, or AME. This calculation is essential for understanding the overall average effect of our predictor variables across the entire population within our dataset. We use the straightforward Stata command, margins dydx union TTL experience. The dydx option specifically instructs Stata to calculate the derivative, or discrete difference, for our variables of interest, union status and TTL experience, for total experience. Examining the output, we find that the dydx for union is 0.185. This translates into a clear, interpretable finding. On average, union membership is associated with an 18.5 percentage point increase in the probability of being a high earner. This provides a much more intuitive insight than the log odds coefficient alone. For total experience, the AME is 0.032, meaning an average 3.2 percentage point increase in probability for each additional year of experience. Our model included a quadratic term for experience, which suggests a nonlinear relationship. To explore this, we use marginal effects at representative values, or MER. We calculate the marginal effect of experience at specific points, 0, 5, 10, and 20 years, using the at option in Stata. The output reveals a clear pattern of diminishing returns. An additional year of experience has a substantial effect early on. For instance, at 0 years of experience, it's associated with a 5 percentage point increase in the probability of being a high earner. However, this benefit significantly diminishes over time. By 20 years of experience, the marginal effect drops to a mere 0.5 percentage points, and it's no longer statistically significant. This crucial nonlinearity was completely masked by the single averaged logic coefficient from our initial regression. While numerical tables provide precise data, graphs are often much more effective for conveying complex relationships and trends. This slide introduces marginsplot, a powerful Stata command that directly visualizes the results from your margins calculations. To generate this plot, we first run the margins command. Specifically, we've used margins union at TTTLX equals 0 to 25 to calculate the predicted probabilities for both union and non-union workers across a range of total work experience, from 0 to 25 years, in 2-year increments. Simply following this with marginsplot then produces the graph you see here. The graph clearly shows the predicted probability of being a high earner against total work experience. We can immediately observe 2 key findings. Union members consistently have a higher predicted probability of being high earners across all experience levels, and for both groups, the probability increases with experience, but at a diminishing rate, eventually flattening out. This visually reinforces the nonlinear effect of experience we discussed earlier. As the final step in our workflow, we focus on presenting these insights professionally. Stata 18 introduces the powerful eTable command designed to create publication-quality tables effortlessly. This command is particularly useful because it allows us to combine results from multiple estimations into a single comprehensive table. For instance, we can display both the initial logic coefficients and the more interpretable average marginal effects side by side. As shown in the Stata code, we first run our margins command with the post option to save the results in memory. Then, a simple eTable command generates a clear output. This table provides full transparency by showing the raw model output, like the logic coefficient of 0.54 for union membership, right next to its practical interpretation, the average marginal effect of 0.185. This way, your audience can easily see both the statistical underpinning and the real-world implications of your findings. To summarize our discussion, the workflow for effective marginal analysis in Stata is a clear 3-step process. First, you fit your model, and critically, you must use Stata's factor variable notation for all your variables and interactions to ensure correct derivative calculations. Second, you estimate your marginal effects using the powerful margins command, carefully selecting the appropriate type, whether it's the average marginal effect or marginal effect at representative values, to precisely answer your research question. Finally, you visualize these effects using marginsplot to gain deeper insights and effectively communicate complex relationships.